Sorry, I had my playlist of 10 hours of uninterrupted whale calls going in the background and didn't realize I never turned it off. Silly Mr. Volel. Anyway, welcome to class 7.4. So we've spent the past 3 classes getting comfy with simplifying polynomials. Now that we've got a good idea of how to use addition, subtraction, multiplication to go forward, next on our hit list is to figure out how we go backwards. In other words, starting with the simplest form, we want to figure out what the polynomials were that would have created it. In other words, the fancy name for what we're trying to do here, thinking back to Unit 1, is a little bit of factoring. So, class 4 of Unit 7, let's get introduced to factoring polynomials. Now, if I want to know what it means to factor a polynomial, a good hint for you might be, well, what is a factor? I want you to look back at your notes as well from Unit 1. The last time that we did factoring, what was it that we were trying to do? And if I'm now trying to do that to a polynomial, what is it that you think I'm trying to accomplish? Go, take a look, tell me what you think, and then we'll chat. Alrighty, so a factor, by definition, is something that multiplies by something else to get me back to a number or a quantity, or in this case, a polynomial that I started with. So if I'm trying to factor a polynomial, really big picture what I'm trying to do is find things that multiply together to get me that polynomial. So my goal is to take my original polynomial and break it down. I want to find the monomials and or the polynomials that multiply together if I were to that would get me back to the polynomial that I'm starting with, that would get me back to my simplest form. So really, what I'm trying to do is to reverse the process of simplifying that I've spent the past 3 classes learning how to do. Cool. So to help orient ourselves when it comes to deconstructing these complex polynomials, let's super quickly remind ourselves of the kind of factoring that we have done. Think for a second about some GCFing. I want to find the greatest common factor of 2 terms. I've got 2 examples here. We're going to do one with just some numbers and one with stuff containing variables. I want to find the greatest common factor, in other words, the biggest thing that both of them have in common. A hint that I might give you, you might want to try to make a factor tree. Give yourself a minute, play around. Can you tell me the GCF of each of these terms? Go! Alrighty, so the hint that I've given you, a factor tree, might make it more obvious what each of these are composed of. So for each set, I'm going to try to break them down. Well, 72, I can pick any factorization that I want. I know off the cuff 72 is even. That means it's divisible by 2. 2 times 36 gets me 72, and 36, well, I know that's 6 times 6, and 6 is, of course, 2 times 3. So I've now fully factored 72. I've broken it down as much as possible. You remember we did a little of this back when we were doing our square and cube roots in Unit 6. Now for 108, same thing. I know it's divisible by 2. 2 times 54 gets me to 108, and I can break down 54. Well, 54 is 9 times 6, and I know that 9 is 3 times 3, and 6 is 2 times 3. For the greatest common factor, I need the biggest possible number that's contained in both. So the easiest way to find the GCF is to think, well, what do these guys have in common? Well, look, both of them have a 2. Both of them also have a second 2. But if I try to take this third 2 over here, there's no 2 that I can pair it with in 108. So that can't be included in my greatest common factor. But I can take a 3 over here as that 3 over there I can pair it with. I can take this 3 over here and pair it with that 3. But I can't take this third 3 from 108 because it does not have a match in 72. So my greatest common factor has got 2 2s and 2 3s So my GCF should be 2 times 2, 4, times 3, which is 12, times 3, 36 is my GCF. With this idea in mind, I can do exactly the same thing for something with variables. As scary as it might seem now, well, let me just begin by chunking it out. I'm going to give myself a chunk for my numbers and a chunk for each of my variables. When in doubt, chunk it out. So I'm going to take these guys, let me split them up to begin. Now I can factor further. Well, 48, I know off the cuff that that's 4 times 12. 4 I can take further, that's 2 times 2, whereas 12 is 3 times 4, and 4 is 2 times 2. U squared, well, that just is a fancy way of saying u times u. Same thing for v squared, right? V squared is just v times v. Now for 60, I can go further. 60 I know is 6 times 10. I can break 6 into 2 times 3, and 10 into 5 times 2. Now u, I can't go any further, but v cubed, this is just v times v times v, and I cannot further break down this w. My strategy is now to look for what we've got in common. Well, between 48 and 60, both of them have a factor of 2, both of them have a second factor of 2, and both of them have a factor of 3. If I tried to take more 2's from the 48 or the 5 from the 60, neither of them have a match in the other guy. So our final answer, our GCF, should have 2 copies of 2 and 1 copy of 3. Notice both of them have a u in common, but I can't take the second u from u squared. It doesn't have a match in 60uv cubed w. Same thing with the v's. Both of them have 2 v's in their factor list, but I can't take that third v from my second. And the w, straggling at the end, does not have a match in my first term, so I cannot include it in my GCF. So I've got my 2, and my 3. I know that they've got 1 u in common, and they've got 2 v's in common. Multiplying back out, well, 2 times 2 times 3, that should give me 12. U, well, that's just u. And v times v, well, that's v squared. So my GCF here should be 12uv squared. Now that I know how to find the GCF, I now want to think about how I would factor it out. So let's refresh our memory with pq plus 2p. Hopefully obvious to you that both of these have a common factor of p. But I know that factoring is really the reverse of what property? What's it really doing backwards? Go, 5, 4, 3, 2, 1. Factoring is the opposite of the distributive property. So I'm trying to find the distributive property problem that when I distribute gets me back to pq plus 2p. You might remember there's a helpful little question that we can ask ourselves. If I'm trying to reverse the distributive property, I'm interested in knowing what must have been inside of the parentheses so that when I distribute back out, I get back to where I started. Well, what must have been inside of the parentheses so that when I distribute, I get back to pq plus 2p? Take 30 seconds, pause the video if you don't already have it. What's inside of those parentheses? Go. And stop. So if I want to get back to pq, well, I would need to multiply p by q. And if I want to get back to positive 2p, well, I'd need to multiply p by positive 2. If you don't believe me, met wet. Let's do some distributive property. P times q, there's my pq. P times 2, there's my 2p. Would you look at that? This guy, I've just checked, is an equivalent expression. I want you to try the same thing with 2, 3, and 4. Let's find the GCF of each of our terms and factor it out using the distributive property. Go ahead. And stop. For number 2, between 2a and negative 4, hopefully you found that both of these have a factor of 2. Again, I'm reversing the distributive property, so I need some parentheses. To get back to 2a, I would have needed to distribute 2 to an a. To get back to a negative 4, I would have needed to distribute to a negative 2. Cool. For 9x squared plus 6x, again, I'm trying to build myself back up to a place where I can do this all in my head. So let me start to think this way. I know that I need something in common between a 9 and a 6. Well, 9 and 6 both have a common factor of 3. So in my GCF, there must be a factor of 3. Between x squared and x, well, x squared has 2 x's. X has 1x. So in my GCF, there must be one factor of x. Both of them have at least one factor. So I'm going to take 3x as my GCF. All I need to know now is what would need to be in the parentheses so that when I distribute, I get back to 9x squared plus 6x. Well, to get from 3x to 9x squared, I need to multiply 3 by 3 to get 9. And I need to multiply x by x to get x squared. To get from 3x to positive 6x, well, that just needs to be 3x times positive 2. If you don't believe me, do your met wet. Make sure that you believe that these are equivalent statements before we move on. And for number 4, again, I want to try to do this in my head. So, number parts. Invisible 1, invisible negative 5, or visible negative 5 really, they have no common factors. So let me look at my r's. There are 2 copies of r in the first term and 8 copies of r in the second term. That means both of them have at least 2. But if I tried to go and take 8 copies of r out of my 2 copies of r, well, that's impossible. So there are 2 copies of r in both r squared and r to the 8th. Between s to the 3rd and s squared, both of those have at least 2 copies of s. So my GCF here should be r squared, s squared. Now, I just need to think, what would I distribute this to so I get back to r squared s cubed minus 5r to the 8th s squared? So to get from r squared to r squared, I don't need to add any more r's in. But to get from s squared to s to the cubed, how many s's do I need? Well, I've got one more s that I need to add to my s squared. Same thing here for my 5r to the 8th s squared. To get from 1 to negative 5, I need to multiply by negative 5. To get from r squared to r to the 8th, well, that's a difference of 6 r's that I need to add back in. And to get from s squared to s squared, well, I don't need to add any additional s's in. Here is my factored form. Now, maybe you've noticed in that last one, there's actually a bit of a cheat code for finding greatest common factors when we're working with variables. Look at the powers in the GCF and look at the powers in your original simplified form. What do you notice that they have in common here? Take 30 seconds. Take a risk, take a chance, make a guess. Go! What do they have in common? And stop. Well, hopefully you've noticed r squared and r squared over here, s squared and s squared over here. I was intentional about saying when I was finding my GCF, both of them had at least some number in common. My strategy when I'm working with finding GCFs of variables, it turns out that all I need to do is take the smallest power that I see on each of my variables. So in this case, I'm going to take the 2 from the r squared because 2 is smaller than 8. I'm going to take the 2 on the power of s because s to the power of 2 is less than s to the power of 3. Magnificent. Now that I know how to find the GCFs, how does this actually help me? Factor polynomials. So say I want to break down something like 3x cubed minus 12x. Well, the first thing that I want to do, perhaps unsurprisingly, as we just did, well, let me see if I can find a GCF. So my first move is always to look for my greatest common factor. There's a fancy name, by the way, for this kind of factoring. I'm trying to do the reverse of the distributive property. So if I'm doing one round of distribution, you might call that single distribution. So I'm going to call this single factoring. I'm trying to undo one layer of the distributive property. Well, between 3x cubed and negative 12x, first of all, can you tell me the GCF? And then can you tell me what must have been in the parentheses so that when I met wet back out, I get back to where I started? Go. 5, 4, 3, 2, 1, and stop. So for 3x cubed minus 12x, I know that to get 3 and 12, right, both of those have a common factor of 3. For x cubed and x, I'm going to take the smaller of the exponents that I see. X here to the invisible power of 1 has a smaller exponent than x to the power of 3. So 3x should be my GCF. Inside of my parentheses, to get back to 3x cubed, I'm missing 2 copies of x, so I need to multiply by x squared. To get back to negative 12x, I just need to multiply that 3 by negative 4. So here is my first step, but you'll notice that there's a second step here that I've written underneath. Take a look at x squared minus 4. Does it look familiar to anything that we might have done, hint, hint, wink, wink, nudge, nudge, in our previous class? What does x squared minus 4 look like? Go. And stop. Well, you'll notice x squared is a perfect square. It's something times itself. 4 is also a perfect square. It's 2 times 2. There's a minus sign in between. Hey, that's a difference of squares. Remember, I can go forward, but I can also go backwards. I can undo the distributive property. So if I can find any of my special products, I should be able to reverse the special product and figure out the factors that would have given them to me. So I've got 2 types of special products. Remind me, what are they? And what would their factored forms have to be? Take 30 seconds, pause the video, look at your notes from 7.3. Go. Three, two, one, and stop. So the first kind of special product that we saw was our perfect square trinomial pattern. It was a binomial times itself. Well, my perfect square trinomials, there were 2 of them. The first one was a squared plus 2ab plus b squared, which you'll remember came from multiplying a binomial by itself, in other words, squaring that binomial, where the sign in between my 2 terms was a plus sign. When it was a minus sign in between, I had a squared minus 2ab plus b squared, which came from multiplying a binomial by itself, where the sign in the middle was subtraction. And I've also got, as with x squared minus 4, we determined that this guy was an example of a difference of squares pattern. Now our difference of squares pattern, it was a perfect square, we called it a squared, minus another perfect square, which was b squared. This guy came from multiplying 2 binomials where the values at the front were the same, the values at the end were the same, but in between, right, one of them was connected by addition and one of them was connected by subtraction. Knowing that x squared minus 4 is a difference of squares, that means I should be able to take it and break it down into a binomial times another binomial. What 2 binomials would multiply together to get me back to x squared minus 4? Well, at the front, these 2 need to multiply to get to x squared. Well, shouldn't it just be x times x, which you'll notice is the square root of x squared. And I can do the same thing at the end, right? I need these 2 guys here to multiply by themselves to get back to negative 4. Well, I know that one of them has a plus sign in front, one of them has a minus sign in front. Similarly, the square root of 4, this would need to be positive 2 times -2. And would you look at that? I've now figured out a way, at least in theory, to reverse the process of simplifying both of my special products from last time. Now, if this feels hard, good. Remember, we're doing stuff that's difficult, so we want to sit in this discomfort. This is just to introduce you to this process. If it still feels shaky, that's totally normal and in fact inspected. We're going to do a little bit more together the next time that we see each other. But until then, sit tight, hang on, we'll get there, believe in you like I believe in you. I promise it's all gonna be okay.